Good morning or good afternoon. We usually do these in the mornings. Excuse me. Geez, it's been a long day already. Good afternoon, everyone. Thanks for joining us. I'm so glad you could all make it. We're covering closed loop system fundamentals today. I'm Sunday Perez, Corporate Marketing Manager for CHC and the Flow Therm Systems Division. And today, your illustrious instructor is Paul Campbell, our CHC Corporate Technical Trainer and guru on this subject. So I'm going to hand it over. Paul, you ready?
Yeah, let's do it.
All right.
Just on the technical side, I live out in the country. We're tied in with Starlink, which is part of SpaceX, which is great internet service. But if there's occasionally we'll drop a satellite for 5 to 10 seconds. So if there's some delay in the slides, I apologize. I'm on my landline, believe it or not. So if my voice isn't perfect clear, I apologize. But that eliminates any delay on satellite. So I'm gonna play dual technology here, if you call it that way. And we'll get started. We'll see. We have some polls to launch, but if those don't come up, it's not the end of the world. So we'll talk our way through as we get there.
All right. I'm gonna start working on that little technical situation.
So we wanted to cover some, basically 3 items that affect us in our hydronic system, things that are in your room, your mechanical space, that you probably don't pay much attention to because you don't have to. But when they go wrong or they're not set up right or they fail on you, it's important to know how to troubleshoot those and the effects they have on our system. So that's what we wanted to cover today. First off, let me start by covering some definitions or fundamentals, if you will. Most of what we do in a hydronic system is considered a closed loop, meaning it's a water running through pipe, and we fill it at one location. We add water to the top of our building, and then we can start to circulate it. We turn a pump on. The beautiful thing about a closed loop system is what goes up also comes down. So our pump in this case only has to overcome the friction loss in the line or our pipe, and then we can start to circulate water. As we move water through our closed loop system, now we can turn our boiler on and we can heat it, and we can take that hot water out to some coils or VAVs, heat exchangers, and we can exchange heat. We can blow air across it, or we can transfer that heat to something else in our system. Snow melt is a good example. I'm looking at about 6 to 8 inches of snow out in the driveway. A snow melt system would be really nice these days. But that's a typical closed loop system. Okay, again, what goes up comes down. We don't care if this building is a mile high or a mile long. We just have to make sure that the pipes are full of water. That's very important. Now, don't confuse a closed loop system with an open loop system. So with open, we're talking about a body of water that's open to atmosphere. And you would see that in an open cooling tower application, maybe a pool job. Something sewage is another good example of that. Something that's got an open pit, and we might have a pump that's pulling water out of that pit and getting that water to the top of our building. In this case, we don't have city water to get water to the top. We have a pump doing that. So this pump is going to generate a lot more pressure than it would if it was operating in a closed loop system. The other thing with open systems, we're dealing with potential for cavitation and other pumping issues, but we'll talk about that more when we get into a pump fundamentals class, okay? But everything we're talking about this afternoon, we're going to consider a closed loop system, just to be very clear, okay? Pieces of pipe that run through our building or our campus and transfer heat. Most of those are controlled with 2-way valves. You may have a 3-way at the end to maintain some minimum flow. So when we come back cold into a boiler, we pick up some heat and we bring that back to our system pumps, where again we transfer that energy and we send low pressure and create high pressure with our pumps and distribute that water flow out to our building, out to our system, okay? A standard closed loop hydronic system. Whether this is a boiler or a chiller doesn't matter. The system really operates the same. Now, a couple things. We're going to be talking about 3 small components in this system. This little fill valve here, an expansion tank, and an air separator, some really basic components, but man, do they have a big effect on what happens out here in your system, as well as how your boiler and pumps operate, okay? We tend to get some blinders on occasion, and when things aren't going well in the system, we focus on the big elephant in the room. First thing we're going to focus on is the boiler or the chiller. If that's operating okay, the next thing we focus on are the pumps. But a lot of times it's little minor components over here that are causing us some pain points. So we just want to make sure we're clear on that so we can build off of this fundamentals of hydronics class. Okay, so that's our intent. Let's talk about this, this first little item that we call a fill valve. Something so stupid that we shouldn't even be wasting any time on this. It's a fill valve, also known as a PRV or pressure reducing valve. We're taking city pressure and we're reducing it down to fill our building full of water and maintain a set or a minimum pressure. That's what a fill valve's doing. You could see this in a residence that has hydronics in it. You could also see it in a light commercial building. If your building gets too tall, you may work outside the range of a standard fill valve, and if that's the case, you might need a mechanical boost, like a pressure booster, to get water to the top floor, okay? But don't be confused here. We've got two PRVs shown. One is a pressure reducing valve, which for the purpose sake, we're going to call a fill valve here, and the other is a pressure relief valve. Totally different purposes, but they're both called PRVs. So be careful if you call in or you go on Amazon and you look for a PRV set for 30 pounds, you might get either one of these that pop up, but they have drastically different purposes in a hydronic system. Oh, look at you, Sunday. We got polls. All right, so let me launch my first poll. All right, we'll give you a few minutes to think that one through, and then we'll share results on that. We're asking about the factory setting here on a standard fill valve. Okay, let's forgive me. Let's keep rolling. Now, what a fill valve is doing for us, it's maintaining the minimum pressure required in our system. Okay, the minimum water pressure. That's when it's cold. That's what a fill valve is doing. A relief valve, on the other hand, is watching out for the maximum pressure. It's protecting that high-dollar boiler or expansion tank, an air separator, a fan coil, anything that's got a max pressure on it. That's what a relief valve is doing. So if we get close to max pressure, this opens up and it sends expanded water or elevated water pressure down the drain. Okay? Let's look at a quick little example here, and we'll reference this for a few slides, and then we'll come to our poll and look at results. We don't do a lot of math in the hydronics industry in general. This isn't a real tech industry. But one of the equations we use on a regular basis, at least at CHC, is this one, that 1 pound of pressure is equal to 2.31 feet, okay? So why is that important? Well, if we know the height of our building, then we can divide it by 2.31 feet and figure out how much water pressure we need in order to fill our pipe full of water. It's that simple, all right? So that's the first thing we need to know is how tall is our building. The second thing we need to account for is the fact that we need a little extra pressure at the top of our building or top of our riser to force any air bubbles out through either a manual or automatic air vent. So typically we need at least 4 to 5 pounds of positive pressure at the top of our riser. The exception here is if we locate our boiler at the top of the building. Most boilers require at least 12 pounds of positive pressure. Okay, so if our boiler is up here, our minimum pressure in the penthouse would be 12 pounds, not 4. That's all we're trying to say here. Okay, let's look at the same example, but let's put some numbers to it. Let's say it's a 5-story dorm. If we use 12 feet per story, that gets us to a total height of our building from the kind of sidewalk level to the top at 60 feet. We're going to take, in order to figure out what fill pressure we need, we're going to take 60 feet and we'll divide it by that 2.31. That gets us to 26 pounds that we need out of our fill valve. Okay? That's going to get water right to the top, but not an additional pressure. So we're going to add an extra 4 pounds to that 26 that we calculated. So in the basement, we need at least 30 pounds of pressure to give us 4 psi up at the top. And that allows us to force air out of solution or air out of our piping. Okay, let me end this poll, and we're going to share some results. Let's see if this is working for everybody. A standard, I should have said pressure reducing valve, but a standard reducing valve comes factory preset at what pressure? We got 19 that said 12 psi. Congratulations, that's the right answer. There's a lot of confusion here, but you're going to see 12 pounds pop up again in this presentation. 12 pounds is what's required to fill a 2-story residence, and that happens to be the pressure that most small PRVs are set for. There are some higher ranges. Even this factory setting at 12 pounds is adjustable between 10 and 25. So depending on the height of your building, you may have to adjust the pressure. Thank you guys for participating in the poll. Again, there are some higher PRVs, so that might be where the 30 pounds is coming from. But yeah, listen, I'm not trying to offend anybody. Just just keep you enlightened. All right, so that's where 12 pounds comes from, is a 2-story residence. Most of the PRVs that we sell are set for that. Now, let's take this 5-story dorm. Let's add an owner's complaint. For 10 years, college students were complaining about how cold they were on the upper floor of this 5-story dorm. And after 10 years, the facility finally decided, hey, maybe we should do something about this. We might have some real problems here after 10 years. So they call in one of our sales guys and they say, hey, we need a new boiler. Okay, obviously we need a new boiler because people are complaining about lack of heat on upper floors. It's got to be a boiler issue. Not necessarily. Our salesman walks in, he sees, hey, we got seems like a really nice boiler for this size building. Let me ask you a stupid question. What's your fill valve set for? Anybody want to take a guess? 12 pounds. When it comes out of the box and you don't adjust it, guess what happens? You fill your system half full of water. Okay? Now, if you're on floor 1, 2, or 3, you are fat and happy. I shouldn't say fat and happy. That's probably not politically correct. You're warm and toasty, okay? Life's good. Listen, you're getting plenty of heat. The boiler's operating. The pump's circulating hot water around your radiators, your coils. You're staying nice and warm. If you're on 4th floor, you might be getting a little bit of radiant heat, maybe some convection heat off the 3rd floor. But if you're up here on 5th floor, you got a great view, but you are freezing your tail off, okay? Believe it or not, this happens more than you think. People slap in a fill valve, forget that they have to do anything with it, and then wonder why their pump's not running so well, or the boiler's not heating the entire building, okay? Or why they can't balance things, or the system's really noisy all of a sudden. It's because we're circulating water and air, not just water. When you fill your building completely full of water, guess what? It quiets down, you can balance it, you get heat transfer, and people are happy in general, okay? So don't overlook the obvious, which is make sure your pipes are full of water. That's all we're trying to get across here. To make matters worse on this job, I know they had no heat on the upper floors. They also had a pump that was rotating backwards for 10 years, okay? It wasn't going the right direction. That's not very efficient. So that's the importance of a fill valve. Talk about expansion tanks. Why do we need this thing we call an expansion tank? Well, when we turn a boiler on and we heat water in our system, that water naturally expands, okay? We have to have somewhere to put that expanded water. If we don't, pressures in our system go up, and we open a relief valve and we send that expanded water down the drain. So If we don't have an expansion tank or it's not set up properly, we turn our boiler on, pressures elevate or climb, our relief valve opens, sends that expanded water down the drain, our boiler shuts off, system cools, our fill valve over here says, whoa, I was supposed to be at 30 pounds of pressure, now I'm at 20 because I sent some system water down the drain, so it opens up. It allows city water to come in and bring minerals and entrained air with it back into our system. We start our boiler again, guess what? Same problem. Relief valve opens, we send more water down the drain. So our chemical balance gets out of whack. Not only that, most boilers are designed to operate in a closed loop system, not an open loop. If we're making up water every time we cycle the boiler and we're dumping it down the drain, is that still a closed loop system? I don't think so. Okay, so the reason we use expansion tanks is to keep our closed loop system closed. Let them expand and contract as we heat and cool water. That's it. It couldn't get any easier than that. Now, there's three styles of tanks. Old school would be a compression tank. More modern would be a diaphragm or bladder style. So I don't want to beat you up on tanks. I've got a few slides here. Let's just talk them through. Okay? The one on the left is a plain steel compression tank, and this guy normally sits horizontally, so it would be laying on its side. More commonly, though, you've got a diaphragm or a bladder tank, and these typically are floor mount. Obviously, this one has a nice big hole in the side of it. That's just a classroom display. Don't let that throw you. It just shows that there's a rubber bag inside the tank. Each one of these, you've got a system connection kind of at the top, and this one is down at the bottom, not to confuse you. And under this rubber cap is where you're going to find a Schrader valve or an air charge to add air to the outside of our bag or diaphragm. Now, a compression tank, you still see a few of these out there. They typically don't get tied in with new design, new projects, but existing buildings, you can still run across these. And picture these as just a big piece of pipe working on a balance of air and water. As we add more water, we're compressing the air. When our boiler cools down, that compressed air forces this water back out into the system. So again, it's just a big piece of pipe with that air that's pressurizing the water that's in the tank. A couple downsides of these. Most facility guys have gauge glass off to the side to show them where the water level sits inside the tank. But this top gauge glass, there's a little fiber gasket up in there. And when it dries out over time, it's a great spot to let all your air escape from this compression tank. Once you lose your air, now you have a waterlogged tank. Now you're popping relief valves on your boiler. The other downside of this style tank is the fact that it's got to be elevated in your mechanical room. It's normally a high spot. So seismically, it can be a challenge. You got a lot of weight over your head. And most guys just don't understand this. It's a very simple operation, but again, it just works on a balance of air and water. All the air that comes out of our system or out of solution should get routed to this plain steel compression tank. If you have automatic air vents around your system, you're stealing air that should be routed back to this tank. So it's just a matter of time before it waterlogs. So if you're having problems with compression tanks, light me up, or let's get a salesman involved, and we can certainly help you there. Okay. More commonly, we're looking at some type of diaphragm or bladder tank. If you look at a diaphragm, it's basically just a piece of rubber that's pinched during manufacturing. So you're going to have water on one side and air on the other side of that tank. Let me back up for just a second. I'm trying to kill you by PowerPoint, but if you come over, if you think your tank's having some issues, if you come over here and check your air charge and you get water out of this fitting, that's clearly a bad day. Okay? If this diaphragm fails or ruptures, ultimately you're going to flood this entire tank with water, and you're going to see it once you open this air fitting. Now, what a lot of manufacturers do with diaphragm tanks, they will put a non-code or residential tank inside an ASME vessel. Clearly, there's no way to service this tank. Okay, if this diaphragm fails or ruptures, it's a pull and replace. There's no way to access it. But you can see this is going to be the water connection that comes in. Water's going to fill or flood this diaphragm. And on the underside here is where we have air pressure. And that's controlled off on this side. Okay, but a tank within a tank is a good way to look at a diaphragm. Now, when we're sizing a tank or reviewing submittals or making selections, one thing to keep in mind is the difference between acceptance and tank volume. Acceptance is basically how much water we can shove into this tank. All right, so in this case, we've got about 4 here that can hold 34 gallons of water, meaning their diaphragm will accommodate 34 gallons. Okay, that's great. That's on the water side. What we also have to think about is what we're doing between a fill valve and a relief valve. Now, forgive me, I have too many things in my hands here. Let me put the phone down for just a second. But if you think about the difference between a fill valve and a relief valve, how much range do we have? So if we have a 12-pound fill and a 30-pound relief, that's a pretty tight range on the air side or the pressure side of our tank. A pretty tight range would drive us into a much higher tank volume. Now, if we have a 12-pound fill and a 125-pound relief, well, that gives us a lot more flexibility on the air side, which would allow us to get away with a smaller tank volume, okay? Acceptance is the same, but tank volume is really based on fill valve and relief valve, that pressure difference. I have a lot of people that say, hey, as long as I meet the acceptance, why do I care about tank volume? Well, if you want to start popping relief valves, just go with the smaller tank volume than what's on the job or what's scheduled, okay? They mean something. Now, you can always go larger on an expansion tank. That doesn't hurt anything. You know, if we're chasing a D200V, a 200-liter tank, boy, we could substitute in a 240-liter tank. That doesn't hurt anybody's feelings. But if you undersize a tank, now you could have some problems. Okay, let's change up. Let's go to a bladder tank. And one way to picture this is just a rubber balloon sitting inside a steel vessel, okay, or a steel cylinder. So you just have a lot of rubber, a big bag, if you will, that's holding system water, and then kind of an air charge around that bag. So this is a typical bladder tank. An advantage of a bladder is the fact that it's replaceable. Now, for anybody on this call who's had to replace a bag or a bladder, I feel you, it is not an easy process. You've got a lot of resistance trying to get a big bag through a pretty tight little collar here. So sometimes you got to lube it up. Sometimes you got to get some mechanical force like a forklift or, in my case, maybe an excavator at home or a come along. You need some help to get this bag out of this tank. It's not an easy setup, but it can be done. Bladder tanks tend to run much larger, so you can run into these for really big campuses, big hospitals, big central plants. They tend to be full acceptance, which means you can put as much water in the bag as you can the tank. So that tank and acceptance doesn't really become an issue on a bladder like it does with a diaphragm. You have to watch it closely. Now, if you're chasing a cheaper tank, but you want it to be replaceable or replace the internals, manufacturers have come up with a reduced bladder tank. So basically, it's a smaller bag that can also be pulled or serviced. There's a collar you remove, and basically you pull a smaller bag out of an enlarged tank. Okay, this is going to work well for a small commercial school. This probably won't play too well in a big hospital or campus setup. It just doesn't have enough volume for you. Which one do you choose? Well, if you're chasing price, diaphragm all day long. Cheapest tank that's, I don't want to say that's out there, but definitely a cost-saving option would be your diaphragm tank. Just remember that if something goes wrong with this tank, you're going to have to isolate it. You're going to have to remove it from the mechanical room and bring in a replacement. There's no way to service it, okay? Bladder is going to be if you're chasing longevity, this is probably your better option because you can service the tank. And the fact that if the bag fails or ruptures, you can pull and replace it without having to physically replace the ASME vessel. And that's a very expensive vessel. Okay, both of these are ASME tanks. The difference is one's serviceable and one's not. Now, one last thing, if you get a bunch of sand or dirt or debris coming in your system, maybe you're off a well pump or just a lot of dirty particulate coming in from the city, you can get some rub points here on a diaphragm, and that can cause it to fail premature. Or in a bladder tank, all that dirt and debris, or sediment, if you will, falls to the bottom of the bag and doesn't create a rub point. So if you have a dirty system and you're going through tanks, a bladder might be a better option for you. One last little tidbit. Most bags, how do I say it, most rubber for either a bladder or a diaphragm, the thickness is about the same. So what do I want to say? I'm talking about longevity. A typical bladder or diaphragm tank is good to about 50,000 cycles. It's a good rule of thumb. That's about anywhere from 5 to 10 years of mechanical service in a typical commercial job. Now think about a cycle. What is a cycle? Well, if you're in a school and you start the boiler up at 5 in the morning, you shut it off at 2 in the afternoon, well, that's one cycle that day, okay? So a typical school might have 5 to 7 cycles depending on in a week. If you're a hospital, on the other hand, and you start your boiler plant and that plant runs 24/7, 365, well, that's one cycle a year. So you would expect a big or a typical expansion tank in a hospital setting to last many, many years. In a school, you're going to be cycling it more, so you're going to be on the lower end. But all you're doing is we're racking up cycles and stretching that rubber in the process. Another thing to think about is how do you restrain a tank? Typically, you're adding some angle brackets to seismically anchor this down to a housekeeping pad so it doesn't tip over in a seismic event. Most of the time you can weld or drill to what we call a collar, okay, the bottom of this tank here. What you can't do is strike an arc to the vessel itself, okay? An inspector considers this tank ASME, but the collar is an exception. So you can drill or you can weld to the collar, but you can't strike an arc to the vessel. Now, you notice that our fill valve was 12 pounds out of the box. Guess what? Air charge in an expansion tank comes factory preset at 12 pounds as well. Wow, look at that magic number. Meaning, if you adjust your fill pressure in the system, you should also adjust the air pressure that's being added to your expansion tank, okay? Assuming that they're on the same plane within the building. We see that misapplied all the time, and it's just a friendly reminder. I've got a couple other slides here on the tanks, and then we'll move on. One thing that's really important, the only time you can check air charge on a tank is when it's isolated from the system and it's drained of all water. That's the only way to get an accurate air charge over here. So if you do this when the tank's full of water, you're going to get what we call a false reading, and it won't be accurate. So you're supposed to isolate the tank, drain it of water, and come back over here and double check your air charge. Let's talk about this tank, assuming it's in our 5-story dorm, and we've got 30 pounds of pressure in our basement. If this tank is also in the basement, well, we're going to have 30 pounds of air added into this tank before we tie it into the system. When the system's cold, we have something called equilibrium, right? We have equal air pressure and equal water pressure. So that diaphragm says, hey, I've got no water in me. That's perfect. That's how we want it. Now we turn our boiler on and we start to add some heat, and water expands. That expanded water go? It goes rushing into our diaphragm tank. That's what it's there for. But as we add water to our tank, we also compress the air that's surrounding it. So our pressure now goes from 30 up to 60. That's okay as long as our relief isn't set at 50. We're we're assuming you might have a relief on your boiler set at 75, maybe 100. Pick a number. As long as your relief's greater than 60, we're okay. Now, when we shut the boiler off, that 60 pounds of air pressure is pushing back on that water, and it's forcing it all back out in the system. So we don't have to open our fill valve. So again, it just keeps our closed-loop system closed. Now, if you run across facility guys or commissioning agents who have nothing to do, no offense if you're on the call, if you make the mistake of checking this air charge on a working expansion tank that's tied into a hot system, you're gonna put a tire gauge over here and read 60 pounds of air pressure, and you're gonna say, whoa, it should be at 30, so let's let some air out. And you come back the next morning and you say, I'll be damned, it's at 60 again. We want 30, so you let more air out. I'm going to tell you it takes about 2 weeks, but eventually you'll let all the air out of the tank. The tank becomes what we call waterlogged, meaning it's full of water but no air to push it back into the system. And now we start popping relief valves on our boiler. And the call we get is, hey, your boiler sucks. It's making a big mess in our mechanical room. Stop touching our expansion tank and problems go away, all right? So guys, that's the importance of an expansion tank. Allows our system to expand and contract.
Hey, Paul, we have a question. Do you want to take it?
Yeah, Sunday, let me run this last, I'll get to the question in just a minute, okay?
Sure.
Now, let's see if I don't know if this is going to work for you or not. I had problems with this last time. Let's see. Guys, I'm gonna play this. Let's see if, oh, that's good. That's good. Hang on a second. Oh, come on. Oh, shoot. All right. You're going to have to take my word for it. So I'm launching a poll right now, and here's the setup for you. It's a chilled water plant, central utility plant. The chillers are running, okay? There's 22 pumps in this mechanical room, anywhere from 100 to 400 horsepower. We're moving a lot of chilled water through the system, and there's 2 expansion tanks, tank number 1 and tank number 2. It's fine to have multiple expansion tanks as long as you tie it into the system at one point, which is what they're doing, okay? We've got a 30-pound fill valve over here. Now, tank number 1 sounds very hollow. It sounds like a gong, okay? It echoes for days if you rap on it. And forgive me, that's what the sound clip's for. Tank number 2, I don't know if this, if you can hear that or not, but tank number 2 sounds very solid. It sounds like hitting your head on a desk after a really angry phone call from a customer. So the question is, which tanker you want to look at? Tank number 1 or tank number 2? It's $12,000 to replace the bag in either tank. The question is, which tank are we most concerned about, tank 1 or tank 2? Now, I'm going to go ahead and stop the poll and share results. We'll talk it through. I always like watching that active as it's going. Well, let's share results real quick, and we'll just talk this one through, okay? Which expansion tank would you want to focus on? Tank 1 that's hollow or tank 2 that's solid? Or neither? Or just spend the $12,000 and let's move on. Now, let's talk this one through. We've been talking about boilers all day long, or at least this afternoon. I'm throwing a wrench at you. This is a chiller, and the chiller's running. If the chiller's running, it means we're coming back from the system at 60 degrees and we're sending 40 or 45 out, okay? We're actually contracting water, not expanding water. So we're going to expect no expansion in these tanks. The only time we have expansion in a chilled water system is when the chiller's shut off and the system heats up to ambient conditions, which might be 90 or 100 degrees on a summer day, okay? So tank number 2 is the one that appears to have some water in it. So how do we troubleshoot that? We isolate it from the system, we drain the tank, and we come up here and we check the air charge. And guess what? Our air charge on this tank was a big 0. Now, where did the air go? We don't know. We just know that somebody lost the air charge on this tank. Maybe it wasn't checked before they installed it or tied it into the system. But all they need to do is add 30 pounds of air pressure to this tank to match the fill pressure and match the air charge on tank 1, and they're back in operation. Okay. Now, looks like I lost my poll. Sunday, are we? Oh, hang on. Hang on a second. Hang on. I think I'm having technical problems, but it looks like I'm back. So bear with me a second. Okay, guys, I hope that makes sense on tanks. Now, I need to.
Paul, we lost your screen.
Yeah, I know. Is it back now, Sunday, or is it still gone?
No, not yet.
Try that. Forgive me, everybody. Sunday, is that working?
No, it says you've started. It's a black screen. So.
New share.
Oh, there we go.
It looks
now it's back.
On my end.
It's
okay.
back. Yeah.
Okay. Give me. Sunday, let me wrap up expansion tanks and we'll get to a question. I'm running a little behind, so forgive me.
Okay. No worries.
Let's talk about tank sizing. And there's 5 things we need to size a tank. The hardest one to get is this thing that we're going to call system volume. That's how much water do we have in a tank. That's a hard one to get. But if we happen to know system volume, then it's a matter of looking at our temperatures. For a boiler, we typically target 40 to 180. And for a chiller, we're typically looking at 40 to 100. And then we also need to know our pressures, our fill, and our relief. Typically, guys, I'm sizing a tank for a 12-pound fill and a 30-pound relief. That's a nice tight band. Gives me my most conservative selection. Okay, let me look at a quick example, and then Sunday, I swear we'll get to our question.
No worries.
Okay, let's assume this is a boiler system sized for 1,000 gallons. And we're going to heat our water from 40 to 180 with a 12-pound fill. And in this case, I used a 100-pound relief. Software is going to tell us, hey, I need about 28 gallons of acceptance, and I need a tank volume that can hold about 36 gallons. Okay, I'm going to keep everything the same, but I'm going to change my relief from 100 down to 30. I'm going to tighten that pressure band. Still heating 1,000 gallons from 40 to 180. So you'll notice that my acceptance stayed the same, but my tank volume more than doubled. Now I'm at 68, 69 gallons, okay? That's the importance of tank volume. Be careful if you're dealing with glycol. It expands at a different rate than water. So if we have glycol in the system in lieu of water, you'll notice that I went from 44 gallons of acceptance versus 28, and my tank volume drove to 109 versus 68. It doesn't sound like a big deal, but if you selected a tank for these conditions, but you're running glycol in the system, your tank's going to be undersized. It means you're going to pop a relief valve or see elevated pressures. Okay, Sunday, forgive me, this is a really good chance to look at some questions before we kind of wrap things up on the air side.
So question from Ryan Callahan, what are some things that can cause a bladder to fail?
Yeah, good question, Ryan. So one of those might be welding slag or debris in a tank. If there's manufacturing debris that's sitting in a tank, then that can cause premature failure. You would typically see that within warranty period or relatively quick. Picture a rod poking through your bag or bladder, that's going to cause it to fail pretty quickly. The other thing would be cycling, but again, you're typically talking 50,000 cycles is a good rule of thumb. If you're failing earlier than that, manufacturers can evaluate the thickness of your rubber with some samples from your bag to tell you what's causing that problem. Obviously, chemical attack is another one. Elevated temperatures can also cause some problems. And the last one I'll throw at you is we have guys who want to install a bladder tank on its side, okay? And yes, you can do that. So this expansion tank, the one on the left here, you could rotate it off to the left because the system connection would be at the lowest spot in the tank. The thing you can't do is rotate this tank to the right because now picture this collar being elevated in the tank. It would put a lot of stress or strain on the internal bag. Okay, so yeah, really good question. We can certainly help troubleshoot if that's the case. But another one might be initial startup. There is a dip tube that goes into this tank. And if your air charge is set too high, you can actually impinge the bladder into this dip tube. So sometimes you have to add a little bit of water premature to prevent that. But all those are kind of, yeah, your key points. Really good question. Sunday, are there any more questions?
Nope, I think that's it.
Perfect.
We're
headed into air management.
I was going to just say real quickly, you can put your questions in the chat box, or there's a little icon that looks like a deck of cards with a Q on it. Either way, I'll catch it.
Yeah, and as always, appreciate the questions. Let's talk about air. If you draw a glass full of water out of a tap, you're going to start to notice some little micro air bubbles that occur, and that's a gift from the city. They give you entrained air. So we get that in our hydronic system. We're constantly dealing with air, and as water cools, it absorbs some of that air. As we heat it, it gives it up. So the hotter the water is, the less air it can hold, and the lower the pressure that water's at, the less air it can hold. Now this is bear with me. Let me launch my. I've got two last polls. Let me launch poll number 3. Forgive me, everybody. Let's try that. Okay, I'm asking about where to put an air separator in a chilled water system. But to help drive this point home, if we fill our system, or our system starts with 50-degree water in it, our system, and it's at 50 pounds of pressure, our system can hold roughly 8% of its volume in air. As I heat that water up, my boiler takes it from 50 to 200 degrees. Now our system can only hold 3.5% of its volume in air. So 4.5% is coming out of solution. How do we deal with that? Do we send it out to our system and let it airlock coils? Yeah, that's probably not the best option. So we do something, we install some air separators. There's some poor man versions of that. One might be a little air scoop, not highly efficient, but would work well on smaller systems. It's basically just an enlarged piece of pipe. So if you've got a 3-inch system connection, this might be a 6-inch air separator or air scoop. So as water comes in, it slows down. Air gravitates towards the top instead of heading out to your system, and then you can vent it out. If you're residential, you might want something a little more efficient. This is a efficient air separator, and it simply and I don't want to say it. It contains what you might consider a chimney sweep. Okay, just extra surface area to catch those little micro air bubbles, and again, vent them out. Connections can either come in from the bottom or from the side, depending on how you want to pipe it. Now, commercially, we tend to look at some maybe bigger air separators. We see a lot of tangential style air separators. Kind of works on a toilet bowl effect. Water flows, in this case, from right to left. So it comes in up the top and kind of swirls around and then exits out. So obviously you have smaller connections tied into a larger vessel. So you're slowing velocity down and you're also swirling it around like a toilet bowl. So all that air collects in the center here and then gets vented out of the vessel. Now these can come with or without a strainer depending on your needs. We see people screw this up. This is supposed to be the bottom of an air separator. This is supposed to be the top. They've got it reversed. Will it work? Yeah, maybe. But this should be rotated 180 degrees. This is your high capacity air vent. Sometimes guys are doing chemical flushes, and that plays havoc with your automatic air vents. So yeah, but typically you're going to hear an air vent burp a few times when you start up your boiler, get rid of the air, and then that's it. You're going to run quiet the rest of the day. So that was a tangential style. More commonly, though, we're seeing a big push in the market to go coalescing. And if you think about it coalescing, it's really more of an inline air separator, and the fact that it flows straight through. There's also a lot of surface area that's packed in here. So you just have a lot of area for air bubbles or air particulate to attach to. So when they get bigger, they start to gravitate up and, again, get vented from the system. Also a really good dirt separator, and the fact that any debris that comes into a coalescing or any air separator heads down to the bottom where you can drain it. Just for reference, this coalescing is about 3 times the cost of a standard tangential style air separator. So it's an investment, but it is definitely more efficient than a standard roll air troll or tangential style. Now forgive me, I know my dogs are going to bark because my wife just got home, so it might get loud here, but I'll talk through it. One thing we have to do, we have to keep the water moving in order to keep air coming back to the mechanical room. If our velocity slows down too much, we're going to get air pockets in our piping. So we just have to watch that. Now let me end this poll. I'll share it. I see somebody raised a hand, but bear with me. We'll get to you in just a second here. Yeah, we got a Mastiff speaking up, so hopefully that doesn't cause you too many problems. Let's look at this poll real quick. Let me share results. I'm not doing great. Here we go. In a chilled water system, where would you want to locate the air separator? On the chilled water supply line just before the system pumps? On the chilled water return line just before returning to the chillers? Sorry, no idea. Typically, we want to remove air at the warmest spot in our system as well as the lowest pressure. In a boiler system, that's pretty straightforward. We leave the boiler, that's the hottest spot in our system, and right before our system pumps is the lowest pressure. So that's typically where you see an air separator on a boiler system. Again, right after the boiler, right before the system pumps. On a chilled water system, it's a little different. Our warmest water is actually coming back from the system before it heads into the chillers to get cooled down. So ideally, you're going to want an air separator on the return side. And I know that question might not have been really clear on that, but that's the intent. You want to remove air as it's coming back from the system and prior to the system pumps. So I hope that makes sense. We're doing the same process, you just locate it a little bit differently. I might flatline you here. How are we doing on, oh, we're doing okay on time. So Sunday, let me power through this, and then we should have another couple minutes for questions.
Okay, that's good.
So let's, I'm going to launch my last poll before I get started here, in case anybody has to go. And yeah, let's talk about where we put these components. We've talked about expansion tanks. Where we tie it into the system, it's pretty important. An expansion tank is the point of no pressure change. Well, that doesn't sound like much, but it, it has a big effect on how things operate. If we fill our system at 12 pounds, and we have 12 pounds of air in our expansion tank, we can't change any pressures. We're assuming there's no boiler in the system, okay? Just an expansion tank tied into a piece of pipe with a pump attached to it. So where our expansion tank ties into the system, it's the point of no pressure change. Now, if you think about a pump, it's a differential pressure machine. It takes low pressure and it creates higher pressure. I know it creates flow as well, but there is a change in pressure. So in this case, if our pump's putting out 14 pounds of differential pressure, means we've got a suction of 12 and a discharge of 26. That elevated pressure is designed to fight friction loss through our valves and fittings. By the time we get back to the suction, we're back at 12 pounds, okay? Everything's good. If we make the mistake of tying our expansion tank into the discharge of our pump, this is our point of no pressure change. It's still saying, hey, we're only going to be at 12 pounds. Meaning if I turn my pump on, my differential pressure machine, my discharge stays at 12. That 14 pounds of differential actually gets taken away on my pump suction. I can drive my pump suction into negative numbers if my expansion tank is located at the wrong spot. So we always want to pump away from our expansion tank. We want to keep it close to the pump. and it's a really good spot to locate our fill valve, okay, or our pressure reducing valve. If we make the mistake of putting our fill valve downstream of the pump, and our pump's putting out elevated pressures, our system might run dry before our fill valve ever opens. So that's no bueno on that. So if I come back to a quick overview, guys, a standard closed-loop hydronic system, we looked at some really small components, but they have a big effect on how the system works. Remember, a fill valve, its only job is to make sure our pipe or our system is full of water. The only time I would ever look at a fill valve is if there's complaints on upper floors, assuming these are they're stacked vertically. If my upper floors were having some issues, first thing I would look at is my fill valve. My expansion tank, when am I going to troubleshoot that? Well, if I'm having pressure fluctuations in my system, or my boiler is popping a relief valve, or I'm making up a lot of water into my system, pretty good indication that I'm sending it down the drain somewhere. And that's probably due to a faulty expansion tank. Either it's failed or ruptured, or my air charge isn't correct, or somebody has valved it off. And my air separator, when would I troubleshoot that? Well, if I'm having some air issues on multiple zones, kind of some sporadic heat or cooling issues, it's more heat than cooling, but if I'm having sporadic problems in my system, it might be that somebody has valved off my high-capacity air vent. We've seen guys put a plug here and put their high-capacity air vent somewhere else in the system. That doesn't work so well either, okay? But all these are minor components, but boy, they have a big effect on how the boiler operates in our system as well as the pumps. Okay, so I hope that helps everybody. We appreciate you taking time, and Sunday, if there's questions, this is probably a good chance for that.
Yeah, I have a couple. So I have one is more efficient air separator needed other than at first system startup. Non-coalescing separator just needs more time to get aired out.
That's a really good question, and that's a great point. Unless an air separator is 100% efficient, you're always going to have even some micro air bubbles that head out through our system and come back for a second or third pass across an air separator. Now, there's been some really good marketing done by the coalescing guys. Spirotherm, who's has done a really good job in the industry, stirring up some issues as it relates to tangential style air separators. Now, I agree with you. You're always going to have some air bubbles that come back to the mechanical room for a second or third time. I'm okay with that. If you're not, if you want to capture 98 to 99% of them on first pass, then you're going to spend some money for a coalescing air separator right out of the box. But yeah, that's a valid point, and I'm not trying to stir the pot there. Thank you for your comments.
Okay. How is expansion tank sizing affected if all elements are located on the roof?
Oh, a good question. To us, it doesn't matter where you locate. Let me bounce out of this real quick. Let's go back to maybe our example here. Let's just pop this one up. If I can do this. Whether we put equipment in the basement or we put it in the penthouse doesn't matter. What does matter are the pressures involved. So if we're maintaining 5 pounds, I'm going to call this a penthouse or upper floor, 5th floor, if you will, and we've got 30 in the basement, that might affect our expansion tank and the fact that our pressure up in the penthouse might fluctuate from 5 to, I'm going to say 20 or higher. In the basement, it might fluctuate from 30 to 50. Really depends on what the relief valve would be of our boiler or our equipment, depending on where it's located. But that's the only system volume would be the same, temperature change would be the same. It's just that little pressure change that you'd have to account for. Just be wary that if you're putting equipment in the basement and you've got a pretty high building, you might see some elevated pressures in the basement, and that's something to watch out for. Most boilers are good for 160 pounds of pressure. Most pumps are good to 175. Most expansion tanks are only rated for 125, as well as air separators. So if you're into a high-rise building, that's why most of the equipment sits up in the penthouse or upper floors. Okay, is to alleviate that pressure that high pressure you'll see in the basement. But yeah, really good question.
Next question is, what's a main reason for air separator fail? Sorry about that.
Separator fail. That's pretty rare, honestly. Most air separators don't fail. They're kind of in for the life of the building. The exception to that might be your high capacity or automatic air vent that is removing air from the air separator. So for the most part, here's an example of a high capacity air vent. It's not great, but that's what this blue thing is sitting on the outlet of an air separator. For the most part, temperatures are fairly stable in the system, unless there's usually stainless inserts in here to collect the air. So unless it's a chemical attack, there's not a lot of issues on an air separator. The dirt is getting separated from the air, so unless you clog this with a bunch of sludge, you're going to have a lot of other system problems as well. So to me, an air separator is pretty resilient. The weak link might be the high capacity air vent that you're tying in with it.
Great. I'm not sure if this is a question or just a statement, but expansion tank total volume size will increase with the tank in the basement?
I don't know if that's true or not, but I'd have to look at some examples to double check that. Yeah, that's possible. I know on a pressure booster side, when we're dealing with hydrodynamic tanks, which are more like a well tank, that we do get more water out of that tank if it's in the penthouse compared to the basement. But I don't know if that's true for an expansion tank sizing or not. I'd have to play with those variables on pressures, but yeah, that might be a valid statement as well. I just don't know offhand, but yeah, I'll take that for what it is. I think that's a good comment, but I haven't run through an example to verify one or the other. But yeah, fair enough.
All right. Does anyone have any other questions or anything they want to throw in?
I will say, let me chime in, Sunday, that if there's other questions or concerns, please shoot us an email, either myself or Sunday. Happy to help. I know Tuesday's class, we had some follow-up. Somebody was looking for some calculations, and we're happy to chime in or happy to assist any way we can.
Great. Well then, thanks everyone for attending. We appreciate your time today, and we look forward to seeing you in future classes. Keep an eye out for an email with a follow-up recording of this session, and also our future class schedule will be going out in the next couple of days with registration options.
Yeah, thank you everybody. Have a good afternoon.